Acceleration of gravity. Acceleration of gravity refers to the acceleration that Earth gives to objects near its surface due to the pull of gravity. Acceleration of gravity is represented by g, a lowercase italicized g. It's important to remember that it is lowercase and italicized so that you don't get it confused with the representation for a gram, which is a g that is lowercase but not italicized. So remember, italicized lowercase g refers to acceleration of gravity, and it has an approximate value of 9.81 meters per second squared. This means that if there is no air resistance or any other influencing factors, the speed of a free-falling object near the Earth's surface will increase by approximately 9.81 meters per second every second. So this is an approximate value. There are some places on Earth where it's a little bit less, it may be 9.7 something. There are some places on Earth where it's a little bit more, it could be 9.86. But overall, on average, you could use 9.81 meters per second squared to calculate something that you needed to use a value of acceleration of gravity for. So it can be different, but the approximate value is 9.81 meters per second squared, and that's what you would use if you were trying to plug it into a formula. For instance, weight is calculated by using the equation W equals mg, which means m times g. W, this little w, is weight. Remember, a big W represents work. Little w equals weight. M equals mass. And the lowercase italicized g represents the acceleration of gravity. So if we had someone or something with a mass of 10 grams, then you could multiply that by meters per second squared, and you'd have to do some work with the units, but that's where you would end up getting your weight from. You would multiply the mass times the meters, the 9.81 meters per second squared. So it's good to know what that little italicized g stands for. And it's just letting you know that the weight is the measurement of force on that object on Earth, near the Earth's surface, due to gravity. So that's why gravity and mass are in this equation together, because it is the relationship between Earth's gravitational force and the mass of an object to let you know how much it's going to weigh here on Earth. Now, objects will accelerate at the same rate regardless of their mass if there are no other influencing factors, such as air resistance. So if two things have different masses and there was no air resistance, let's say we could put two things in a vacuum. If we could put a giant boulder and a feather in a vacuum where there was no air resistance and we dropped them, they would both accelerate at 9.81 meters per second squared and land at the same time on the ground. However, there is air in the Earth's atmosphere, so air resistance is usually a factor. And it can be affected by the size, shape, and velocity of objects, but not mass. So, if something is bigger and it has a flatter shape, it's going to hit more air and have more resistance from the air. If something is long and narrow, it's going to have less air resistance. If something is being thrown versus dropped, then that's going to be a velocity difference. But the mass isn't going to matter as much. the mass isn't what's going to affect the air resistance. Now, mass does kind of play into this. If you have two boxes that are exactly the same size, one is empty, one is full. When you drop them, the mass of the full box is going to be able to overpower the force of air resistance, so it will land a little sooner because it was able to overpower and overcome the force of the air resistance, where the empty box wasn't able to overcome it as well. But if we were in a vacuum with no air resistance and we had a full box, empty box, same exact shape, and dropped them, they'd land at exactly the same time. So in our normal everyday conditions, air resistance is going to be a big factor. The size and shape of your objects that you're comparing and whether they were dropped or thrown are going to have an effect on the acceleration of your object, how fast it's going, and how quickly it's going to be able to accelerate toward the ground. But you can still use 9.81 meters per second squared as a basic rule of thumb for the gravity, the acceleration of gravity that Earth is going to put onto objects with no other forces interacting. So it's still a good jumping off point. You would start with 9.81 meters per second squared and then try to figure out the effect air resistance had, because the basic acceleration of gravity on Earth with no other influencing forces is going to be 9.81 meters per second squared.
Boyle's law. Boyle's law is named after a physicist, Robert Boyle, who discovered the relationship between pressure and volume of a liquid. And Boyle's law says that pressure times the volume is equal to a constant. In other words, pressure and volume are inversely proportional to each other at all times. Another way this could be written would be that P is equal to C over V, if you're more familiar with inverse proportion laws. So what this is saying is, so let's take an example. Let's say that we have a pressure of 25 pascals. Pascals is the unit for pressure, and a volume of 5 liters, and that's equal to 125. So our constant in this case, C, is equal to 125. The constant changes, but we know that it always stays constant. So in this case, if our pressure drops to, say, 10, well, then we have 10 times our volume is equal, we know it's equal to 125. Now, if we use algebraic rules, we can divide both sides by 10, our 10s cancel, and we can figure out that our volume is equal to 12.5 liters instead of 5. So we see that increase in volume when our pressure decreased. That can be depicted over here in this image here. We have our initial one. So in this case, we have a high pressure. This is 25 pascals. And over here, our pressure dropped, but our volume increased significantly. So that's an overview of Boyle's law. Now, to use that in an example, we have an example down here. A 2-liter balloon has a pressure of 101.5 kilopascals. When the pressure increases to 1,015 kilopascals, what is the volume? So we have a P1. We have our pressure 1 is equal to 101.5. Our P2 is equal to 101.5, so 1,015. Our volume 1 is equal to 2.0, and our volume 2 is what we don't know. So that's what we're shooting for, to figure out our second volume. So I'm going to get some of this out of the way and we'll work it right here. Now there's two ways we could work this. We could work this from this first one, the P1 and V1, and solve for C. Or because we know that they equal the same constant, we can actually take P1 V1 is equal to P2 V2. And what happens, because we know what we're looking for, our second volume. So what we can do here is we can actually divide. We can solve this before we plug in any of our numbers. And our P2 cancels. So V2 is equal to P1 V1 over P2. And we plug in our numbers there, and we get 1015 times 2 over 1015. Now, when we do all our solving, we get that volume 2 is equal to 0.2 liters. So we had a decrease in our volume to 0.2 liters. And that is Boyle's law.
Today we want to go over just some of the basics of chemical reactions. We don't have time today to do this thoroughly or fully in depth, but just want to go over some of the basics of chemical reactions. So when we think about chemical reactions, one of the things we ought to think about is time scale. How rapidly or slowly do chemical reactions take place? And in terms of time scale, obviously we're measuring this from our vantage point, from our viewpoint, so on the human time scale, the way we experience time. Chemical reactions can happen very rapidly, very quickly, and also very slowly. From the lower end, just fractions of a second for a chemical reaction to take place, all the way up to the upper end, years and years and years and years and years before a chemical reaction fully takes place. And everything in between. So with chemical reactions, the time scale is from fractions of a second all the way up to lots of years for them to take place and everything in between. When we think about timescale, we also think reaction rates. What affects reaction rates? So in a chemical reaction, we need to think in terms of the frequency of the contact between the chemical components that are reacting. If it is very little contact, you have a slower rate. If they don't come into contact very often, that also slows it. If there's a great mixing of these things that react volatilely, you can have a very rapid reaction. So it's the frequency of contact between the interacting chemicals. The temperature plays a role. Higher temperature, lower temperature can affect not only the reaction but the time rate as well. And then the properties of the chemical that is interacting. Is it a solid, a liquid, or a gas? The shape it's in. All of these things play a part in reaction rates. Frequency, temperature, and properties. Then when we think about reaction rates, you can actually influence those rates. You can accelerate a reaction rate. This is called using a catalyst. A catalyst is introduced into that chemical reaction, which greatly speeds it up. And that's the catalyst's only job, is to come into this interaction between these chemicals and to speed up that reaction that would ordinarily take place over a slower period of time. You rapidly increase it. But you can also decrease reaction rates, and this is called using inhibitors. If you introduce an inhibitor into a chemical reaction, it slows it down. It keeps them from reacting as quickly. So you can affect reaction rates not only naturally and through ways that you're able to control temperature and what form it's in, things like this, but you can also introduce other chemicals, catalysts to accelerate and inhibitors to decelerate the reaction times of the chemical reaction. Now, chemical reactions can, when they occur, release heat, release light, electrons, ions. There's usually some form of product from this interaction, this chemical reaction that's taken place. Sometimes chemical reactions send the temperature in the opposite direction, but usually it's things like heat and light, electrons being traded or spun off, ions, radicals going off, things like this. And then finally, heat and other factors can influence chemical reactions and help break bonds. If you think in terms of breaking down carbon bonds, this is done obviously in the production of oil and related materials. You've got strong, stable carbon bonds that need to be broken down and split up. Heat is usually a thing that is primarily used to help break those bonds, divide those things up, and then sort them out to their various functions and purposes. And if you ever do any sort of research or study, it's very fascinating to look at an oil or a chemical plant and how they bring in the raw materials using heat and other pressure and things like this to break up the raw material that's brought in into various other materials, sifted out and sent other places and put to other uses. It's fascinating. But anyway, chemical reactions then, just the basic overview again, time scale from fractions of a second to years and years and years. Reaction rates are affected by the frequency of contact, the temperature at the point of their mixing and their contact, and then the properties, solid, liquid, gas, the shape of it, these sorts of things. Reaction rates can be accelerated with catalysts, decreased with inhibitors. Chemical reactions produce things often like heat, light, spinning off electrons, ions, things like this, and heat and other factors influence chemical reactions and help to break bonds. Once again, this has just been the basic overview of chemical reactions. If you'd like to learn more about this or related matters, underneath this video you'll find a link. If you'll click on that link, it'll take you to the website that has that information, and while you're at that website, you'll also find a link to an ebook that's ready for immediate download. Today we're going to go over combustion and terms and concepts related to it. So if you look at the board behind me, we'll just start at the top here. When we talk about auto-ignition temperature, when we think about auto-ignition temperature, we're talking about the temperature at which a substance is so hot that it just bursts into flame without need for an ignition source. As things get hotter and hotter, most substances, though not necessarily all, have a point at which when they reach that temperature they will, if there is oxygen or other medium in which it can burn, burst into flame on its own without the need for an external source of combustion, heat, fire, anything like that. It just on its own, spontaneously. And so it would be tied into number 5 here, spontaneous combustion, no source of ignition. When we think about things that don't need a source of ignition and yet burst into flame, we can think in terms of maybe a compost pile. As the compost pile sits there, it's got hay and other things in it probably. It's strongly insulated, and there's fermentation going on inside of it through the bacteria, which is generating heat. And as the heat rises because of the insulation, there's nowhere for it to go. It eventually reaches a temperature at which ignition can take place without an outside source, and it bursts into flames. And so sometimes people do have compost piles that go up in flames because of the spontaneous combustion medium, the fermentation by the bacteria, raising the temperature, it's well insulated, and then boom, up it goes. When we think about combustion, we have certain types of reactions. Exothermic reactions are those that give off heat. They generate heat and force it out, sometimes light, sometimes noise in the form of explosions, but exothermics give off. Endothermic absorb or take in heat in these kind of reactions. So there is a heat transfer taking place here. Exothermic forcing it out, endothermic pulling it in, absorbing heat inward. When we think of endothermic reactions here, you can think of these sports medicine instant cold packs that has a chemical reaction inside them that gets very cold very quickly. This is an endothermic reaction. So when we think about heat transfer, which is very much a part of combustion, we need to remember that what's going on is within the way physics works now, thermal equilibrium is always trying to be sought. So if there's something that's warmer next to something that's colder, the general motion will be that the warmer temperature will move towards the colder temperature until these reach equilibrium. If you think here of a rod that's been superheated on one end and is room temperature on the other end, what's going to happen then in conduction with this thermal transfer is the kinetic energy from the rapidly moving molecules and atoms down here on the hot end running into the colder ones, transferring their heat and energy that way, and so the heat moves down from the hot end towards the cold end, eventually reaching a place of equilibrium where this loses its heat, this gains the heat, and then they match. So heat transfer is very much a part of combustion. Conduction being one of those things, direct molecular transfer of heat until thermal equilibrium is reached. Another form of heat transfer is radiation. This is electromagnetic wave transfer of heat. Here we need to think in terms of the sun, which gives off electromagnetic waves or radiates radiation, and it heats the earth. It communicates it through the medium of a vacuum, space, but it still arrives here in the form of heat transfer, radiation, as it warms the earth and strikes the earth. So that would be a form of heat transfer, radiation. And then convection. Convection is heat transfer through a fluid medium. Now when we say fluid, we don't automatically mean liquids. Fluids are also gases. So a fluid medium is a gas or a liquid. So you can get convection currents in air as well as in water. What you have then is heat is applied to the fluid, either gas or air, and as the fluid is heated, it gets less dense and warmer, and so it rises, causing the more dense, colder fluid then to move downward, and you get a circular motion. If we think in terms of boiling water, you can actually watch as it seems to churn up from the bottom. The heat source is there. The hot water becomes less dense, lighter, comes to the surface. The cold water sinks down, is heated, and comes up again. You can think in terms of air as well. Hot air, less dense, lighter, rises, cold air, more dense, heavier, sinks, is heated, and sent around. So you get these circular convection currents. So these are the main things to keep in mind around heat transfer: conduction, direct molecular radiation, waves, convection, this circular motion through a fluid, medium, gas, or liquid. We talked about spontaneous combustion in your compost pile under auto ignition temperature, and then we've got hypergolic reactions here, or combustion. Basically, that's a substance when brought into contact with another substance that immediately ignites without an ignition source necessary. It's just that type of reaction, and this is what they do in rocket engines. They have two separate substances kept in different compartments, and then they are injected into a third compartment at the same time, and when they meet and react, you get combustion automatically without an ignition source, which then they use to propel the rocket upwards. So hypergolic substances are those that ignite or combust when brought into connection with an oxidizer. So this substance brought into an oxidizer immediately combusts, and of course you get rocket explosions directed beneath the rocket, which sends it up. So hypergolic combustion. Well, this has just been a brief overview then of things related to combustion, some of the concepts, some of the vocabulary in those concepts. If you'd like to learn more about this and related matters, if you'll look underneath this video, there's a link down there. And if you'll click on that link, it'll take you to the website that has that information. And while you're on that website, you'll also find a link to an ebook that's ready for immediate download. Today, in our video, we want to go over a simple concept in physics called displacement. Physics may sound scary, but it really is just the explanation and description of the way matter moves. The explanation and description of the way matter moves. So when there is a change of a piece of matter, a brick, from one location to another location, we have had what in physics is called displacement. Change in location from one place to another of some matter. Hitting a golf ball, displacement. It starts on the tee and it ends wherever the shot ends, and that movement of the ball starting on the tee and ending up out in the fairway, hopefully, in physics is called displacement. Now when we think about displacement, we can actually write it out and describe it mathematically, and this is what makes physics so great. It's a mathematical description of the motion of matter and can be very precise, which is very helpful. So displacement then is the final position of the golf ball in the fairway minus the original position with the ball on the tee. And we often talk about that in terms of, hey, he just drove the ball 280 yards. So that 280 yards is a description of the displacement of the golf ball 280 yards down the fairway from the beginning point on the tee. Final position minus the original position, 280 yards. And when we talk about it in those terms, just the size of that displacement, the distance traveled, that is a scalar quantity. Scalar is magnitude or size alone. We didn't talk anything about direction. Did it go 280 yards down the fairway straight, or did it hook, or did it slice? Did it go 500 feet straight up and then come down? We didn't talk about direction at all. We just measured the size or the magnitude. So magnitude equals size or the measurement of the displacement, 280 yards. Now when we add direction to the magnitude or size, we get what's called a vector. So the difference between vectors and scalars is the difference between having the magnitude alone or having the magnitude plus the direction. And I've got some examples here on the board that we're going to look at. If I say something was moved 5 meters to the right, I have both magnitude, the size, in this case the distance moved, 5 meters, plus the direction to the right. 5 meters to the right is a vector because it has both magnitude and direction, both a distance measurement, a size, and the direction in which it went to the right. Now, if I tell you 32 degrees centigrade, all I've given you is the magnitude, the size of it alone. I haven't talked about any sort of direction of that temperature up or down. So that would just be a scalar. 32 degrees centigrade is a scalar. If I talk about 5 meters without giving you any direction, I've given you another scalar. If I talk about 256 megabytes, I've given you a scalar. I haven't given any change in direction, any change in the direction it's gone in the amount, lesser or more. All I've talked about is here magnitude, the size. Now, if I say we traveled 5 miles north, I've just given you a vector. Magnitude, the measurement here, the size, 5 miles, and direction, north. And so when we think in terms of the golf ball, if I just said he drove it 285 yards, I've given you a scalar. But if I said he drove it 285 yards straight down the fairway, I've just given you a direction as well and a vector. Displacement, once again, is the main thing to take away from this video. That is the movement, the change in location from one place to another of matter. So the change from one location to another is called displacement. Think of a golf ball. Think of picking up and moving a box. Matter moving from one place to another, and displacement can be described, once again, it equals the final position minus the original position. Within displacement, we can talk about scalars and vectors. The difference between them being that vectors also include direction, whereas scalars only have magnitude. All right, well, that's just been a basic overview, and I do mean basic, of the very elementary concepts in physics related to displacement. And if you'd like to learn more about this or related matters, if you'll look underneath this video, there's a link down there. If you click on that link, it'll take you to the website that has that information. And while you're on that website, you'll also find a link to an ebook that's ready for immediate download.
Friction. Friction is the force that results as a resistance to motion where two surfaces are in contact. So if two surfaces are touching, there's going to be friction between them. If I'm holding my hands together, there's friction between them if I rub them. If I'm holding this remote, there's friction between my hand and the remote as I try to slide it across. So friction is just that force that results when you try to move two things against each other whenever two surfaces are touching. Now, friction can be calculated using this formula. And in this formula, this lowercase f represents friction, what you're calculating. The uppercase f with a little c is the contact force. So the C stands for contact. The big F is always going to stand for force. So the contact force between the two objects. So just their basic resting force right here. Me holding this remote on my hand, there's a force between them. There's a force against my hand by the remote. There's a force against the remote by my hand. They're pushing against each other as they are sitting here. So the contact force is right here. The weird looking little U is a symbol that represents the coefficient of friction based on the material's compositions. So what each one is made of. So there's going to be a specific coefficient between skin and plastic. And multiplying the contact force of these two objects by the coefficient of force between, or the coefficient of friction between plastic and skin, you would be able to get the friction that would result between these two items. There are several different kinds of friction. We're going to talk about two kinds that exist between dry friction. Now, there will be friction between different liquids. Two surfaces don't necessarily mean two solid surfaces, but we're just going to talk about dry friction today. So static friction is one type of friction that can result with dry friction, and it exists when a small amount of force is exerted, but neither object actually moves. So if I were to push on this remote, I'm applying a force right now, but the remote is not actually moving. So this is a static force because I'm pushing. I can feel the pressure on my hand where the remote's trying to move, but I'm not putting enough force that it actually moves. So this is a static friction right now. The other type of dry friction is kinetic friction. And this exists when a larger amount of force is exerted and one of the objects does move. So, if I push the remote hard enough that it actually moves on my hand, this is kinetic friction. It's actually moving on my hand. If I'm pushing and it's not moving, static friction. If I'm pushing and it moves, kinetic friction. Static, no movement, not pushing hard enough. Apply a larger force and it actually slides along my hand, kinetic friction. So the friction of staying still but applying force is static. The friction of two objects actually moving against each other is kinetic. Now generally, static friction will be greater than kinetic friction, even though you may think, oh, well, if you're actually moving the object, it's going to be more. That's not true, because the amount of force needed to keep an object moving is actually, usually, less than the force needed to get it started. So it actually took a bit more force to get this started moving than it does to keep it moving. So once I get the remote moving, it's not using as much force, and so my static friction was actually going to be greater than my kinetic friction. So while I'm pushing here trying to get it to go, there's more friction than whenever I've actually got it moving. So once I've gotten it moving, it's easier to keep it moving than it was to get it started, which is what that means whenever we say the static friction is going to be greater than the kinetic friction, which means the force pushing on an object where you don't get it to move yet is going to be larger than the friction whenever you're pushing on the object and you do get it to start moving. So friction is just that force that exists between two objects that are touching whenever you try to move them. Any two objects that are touching, if you try to move them against each other, you will kind of feel that force, and that is known as friction.
Today we're going to briefly overview heat transfer on the molecular level, or what is known as thermal conduction. Thermal conduction. This is the transfer of heat from the collision of molecules or the interaction of atoms within a substance, a solid, a liquid, or a gas. And we're going to, for our example purposes today, use solids to talk about the concept of heat transfer or thermal conduction. Basically what happens is when an object is heated, heat is applied. In this case we have a frying pan sitting on a stovetop. Heat is being transferred into the frying pan, and here we'll just say it's a cast iron skillet, so it's all metal. At first, the handle out here is cool. It can be picked up with the bare hands, no problem, but the heat that is coming here up into the bottom of the skillet is going to be transferred throughout the entire body. As these atoms interact with the other atoms over here, as the molecules interact, heat is transferred. The collisions transfer heat and energy. That heat and energy then continues to be transferred until it spreads throughout the entire object. If the heat is taken away, what you'll find then is that the heat will transfer throughout. The hotter areas will get cooler, the cooler areas will get hot until you reach a state of equilibrium where basically there's a uniform temperature. But the whole idea here of heat transfer at the molecular level is when heat is applied, the molecules in the object, in this case the frying pan, are agitated as they move and collide with the other molecules and atoms. Energy and heat are transferred, and because of that, what is ordinarily a cool spot out here will get warmer. The heat will transfer throughout the object because of those interactions. Another example of this, showing that the temperature, the heat is transferred, but no transfer of actual matter takes place, is when you place a hot coffee cup on top of a desk or a table. So the liquid inside the hot coffee, inside the coffee cup, doesn't actually exchange molecules. The coffee and the cup don't interchange, but the heat is transferred to the cup and from the cup to the desktop, so that when you lift the cup up, there's usually some sort of condensation underneath it, or you can put your hand on the surface and suddenly it feels warm. This is because there has been thermal conduction or transfer of heat from one to the other. So the basic idea is that heat transfers, not actual matter transfers, and it's due to the interaction of the molecules or atoms. As they are heated, they're agitated, they bump into the other ones. This collision transfers energy and therefore heat, and it spreads throughout. This has just been a basic overview of the basic idea of thermal conduction or heat transfer at the molecular level. If you'd like to learn more about this or related matters, underneath this video you'll see a link. If you'll click on that link, it'll take you to that website where you can get that information, and while you're on that website, you'll also find a link to an ebook that's ready for immediate download.
Heat versus temperature. Heat is energy transferred from one body or system to another due to thermal contact. And that just means contact between two things where the temperature is going to change. And that is because energy is being transferred between the two objects. The transfer of heat energy from hotter to cooler objects is accomplished in three different ways. It's accomplished by conduction, convection, and radiation. Conduction is the direct transfer of heat from one substance to another. So the two substances or objects must be touching. It's a direct transfer. Examples would include ice melting in your hand. Your hand is touching the ice and transferring its heat energy, making the ice melt. Another example would be burning your hand on a hot pot. So if this pot was on the stove, it gained heat energy from the stove, and then if you touched it without any kind of protection on, your hand would be burned because that pot's heat was transferred to your hand and it was too much for your hand to handle. So those were results of direct contact. Another example, another way that heat energy is transferred is through convection. And convection is the movement of matter due to density differences caused by temperature variations. So that means that, this is usually related to heat transfer through liquids and gases. So that's going to mean that if you have a warmer liquid or gas, it's usually going to be less dense and rise up. If you have a cooler liquid or gas, it's usually going to be more dense and it's going to sink down. So warm air or gas or liquid is going to rise up, cool is going to sink down, and that's because cooler objects, cooler liquids, gases are going to be more dense and sink. Warmer liquids and gases are going to rise up. They're going to be less dense. Examples of that happening are the greenhouse effect, the gases moving around in that enclosed space are going to move the warm air around and keep the whole area enclosed in glass warm, even though it's only the sun that's kind of heating things up close to the glass. The warm air is going to circulate. Another example is how you've got warmer water on top in swimming pools and lakes, and that's because cooler water is going to sink down, warmer water is going to rise to the top. Now again, the sun is going to have some effect on warming up that water, but if you were to get in a pool at night without the sun being there, the warmer water is going to be on top and the cooler water is going to be at the bottom. And that's because that cooler water is denser and it's going to sink. if you get into a pool or a lake, every once in a while you might find a cold spot with your feet because your feet are going to be touching deeper down where the cooler water has sunk down because it's denser. And that's an example of convection. Similarly, having warmer upper stories in a building, in your home, in an apartment, and cooler lower stories. So if you live on the first floor of a building, it's often going to be cooler because all the cool air is going to rise or is going to sink down to your floor of the building. If you live on the very top floor, it's often going to be warmer because everyone's warm air is rising up to the top. Plus, you're getting hit with the sun without as much insulation. So convection has to do with temperature difference causing difference in density, and that causing air or liquids to circulate, always with the cool sinking to the bottom and the warm rising to the top. The last way that heat energy is transferred is through radiation. And radiation is the transfer of energy through empty space as electromagnetic waves. And the examples we have of that will kind of explain what that means. The sun is an example of that. You can feel the heat from the sun, but you can't see anything coming towards you. You don't feel something touch you. There's no direct contact. It's not about the air moving. It's about the sun's electromagnetic waves sending that radiation down, and you feel it as heat. Another example would be with a light bulb. If you put your hand near a light bulb, it's going to be hot. If you don't touch it, you're still not having direct contact, but you can feel the heat around the edge of that light bulb. And you can't see it moving the air around. It's not moving anything around that way. It's just that the light itself is creating heat, and it's sending out heat in the form of radiation. And another example would be a campfire. Same thing. The flames are creating heat. You don't have to touch the flames directly to get the warmth. You can just feel it because it moves through the air. Now, there is some convection involved with that as well, and with a lot of these things, they can kind of work together to transfer heat. But just to give you examples of how each one is different, that's what we are trying to do here. If you'll notice with radiation, a lot of the time it involves some kind of light as a heat source. And that's where your energy is being transferred from. Convection, a lot of times, is going to have to do with liquids and gases, and conduction has to do with direct contact. You actually have to be touching whatever it is that you're supposed to be getting heat transferred from, or that you're supposed to be transferring heat to. So, that's what heat is. The energy that's transferred from one body or system to another. And this is done usually hotter to cooler, and by conduction, convection, and radiation. Now, temperature is the measure of an object's stored heat energy. So how much heat energy could this object give off if it touched something else, or if it were to release some of its heat energy via convection or radiation? So that's what temperature is. It's the measure of an object's heat energy that's stored within it. When the temperature of an object goes up, its atoms move faster, and that increases its kinetic energy. So warmer items are going to have a higher temperature and therefore more heat energy stored within them. Cooler items have a lower temperature and they're going to have less heat energy stored within them. And we use thermometers to measure temperature. So, heat is energy transferred from one body to another. Temperature is the measurement of how much stored heat energy is in an object. Mass, weight, volume, density, and specific gravity. These are all important terms that you'll find in physics, and it's important that you know the difference between each one. First, we have mass. Mass is a measure of the amount of substance in an object. So, how many atoms or molecules of that one substance are in a specific object. That's what your mass is. Where weight is a measure of the gravitational pull of Earth on an object. So let's look at our example over here. We have this rectangular prism, and it measures 8 centimeters long, 3 centimeters wide, 5 centimeters high. So its mass, I'm just going to tell you, is 10 grams. Its weight is 1 pound. And in the United States, we measure weight in pounds. Other countries have different units of weight, but pretty much all of the scientific community is going to use grams and the metric system as units for mass. So 10 grams tells us that we've got 10 grams of a substance in this box. The weight says that we have 1 pound of gravitational pull of Earth on that box. Now, this is the gravitational pull of Earth, which means that on different planets or different entities in our solar system, the weight would be different. For instance, on the moon, there is less of a gravitational pull, so your weight would be lower on the moon. On other planets that are further away or closer to the sun, you're going to have a different gravitational pull, so you would weigh more or less on different planets because the pull would be different. But whenever you see a weight listed, it's going to be the gravitational pull of Earth on an object because that's where you are most likely to find these things. Let's move on to volume. Volume is a measure of the amount of space occupied. And there are many formulas to determine volume. It's going to depend on what shape your object is, how you're going to determine its volume. For instance, the volume of a cube is the length of one side cubed, or s cubed, side cubed. And the volume of a rectangular prism is length times width times height, or L times W times H. And in fact, that is the same formula you could use for a cube. One side times one side times one side. Just in a cube, it wouldn't matter which side you picked because they're all the same length. In a rectangular prism, it's important to make sure you take the length of a side times the length of the prism times the width of the prism times the height of the prism. You can't just pick any 3 sides. The volume of an irregular shape can be determined by how much water it displaces. So say you have a rock and you want to know what the volume of this rock is. How much space does it take up? Well, most of the time a rock is not going to make a perfect sphere, so you can't use that formula. It's not going to make a perfect rectangular prism or cube unless it is formed that way and ground down to be a specific size. Most of the time, you're going to find an irregularly shaped rock. So let's look at how water displacement can help us with volume. If you fill a beaker with some water, let's say we start with 20 milliliters of water. Then we drop our rock into the same beaker, and now our water reads 47.5 milliliters. Well, you didn't add any more water. What you added was the rock. So the difference between the new volume and the old volume is going to be the volume of your irregular object. So our rock that we dropped into the water, we can take our new volume, subtract our old volume, and it's going to tell us the volume of our rock, our irregular object. So the new volume was 47.5 milliliters. The old volume is 20 milliliters. And so we take our new volume of 47.5 minus the old of 20 and get 27.5 milliliters. So that would tell you the volume of this rock. And there are different units of volume as well. It is not always given in the same units that width and height and length would be given in, but it can be given in more of a liquid measure since we did measure it this way. Now, a milliliter is also the same as a centimeter cubed, so you could at the same time translate that to 27.5 centimeters cubed. But since we did it with water displacement, I'm going to leave it milliliters. Now let's come back to our example and find our volume. So our volume is going to be length times width times height. So let's take those. 8 centimeters long times 3 centimeters wide times 5 centimeters tall. All right, 8 times 3 is 24, and then we have to multiply times 5. 5 times 4 is 20, 5 times 2 is 10, plus 2 is 12, and so we get 120 centimeters cubed. So whenever we multiplied the centimeters out, it turned into centimeters squared and then centimeters cubed. So your answer for volume is going to be given in cubic units, and so this is 120 cubic centimeters or centimeters cubed. That is our volume of this object. Now let's move on to density. Density is the measure of the amount of mass per unit volume. So they want to know how much substance is there per the space that it makes up. So some things are going to be more dense. Their particles are going to be smashed more closely together in a smaller unit of volume, where some are going to be more spaced out and they're going to be in a bigger unit of volume. So density is going to tell us how much mass there is per volume, per space that an object is taking up. So the formula for density is mass divided by volume, or D equals M divided by V. And it is given in terms of mass per cubic unit, such as grams per cubic centimeter. Grams per cubic centimeter. So let's find the density of our object over here. So we have our mass, which is 10 grams, and we have our volume, which is 120 cubic centimeters. So now we just have to reduce, and what we're going to end up with is being able to cross out these zeros, and we're going to have 1/12 gram per cubic centimeter. And we can turn that into a decimal because that's usually how we like to see things. So I'm going to do the division up here. So we've got 8 times 12 is 96. We've got 4 left over. Twelve goes into 43 times and we get 36. And this is going to keep on repeating. So we've put another 0 and come down, we get 40 again. So it's 0.083 and it's going to repeat. So we're just going to go to 3 units. So our density would equal 0.083 grams per cubic centimeter. Okay, so our object has a density of 0.083 grams per cubic centimeter. That was based on its mass of 10 grams for a volume of 120 cubic centimeters. Next, let's move on to specific gravity. Specific gravity is a measure of the ratio of a substance's density compared to the density of water. So the specific gravity of a substance would be the density of the substance divided by the density of water. Now, the density of water at room temperature is 1.000 grams per cubic centimeter. If you divide anything by 1, it's going to be itself. So as long as you're at room temperature, the specific gravity of an object is basically going to be its density. But as water gets cooler or hotter, its specific gravity is going to change a little bit. And so specific gravity can change based on air pressure, based on temperature, based on any other physical elements that are going on in the area where you're trying to determine specific gravity. So water isn't always going to be 1 gram per centimeter cubed, but at room temperature, it will be. And so as long as everything's at room temperature, regular pressure, then you're going to have your specific gravity be basically the same as your density of the substance. Now, if your specific gravity is greater than that of water, so it's greater than 1 gram per centimeter cubed, then your substance is going to sink. It is denser than water, it's going to sink below the water. If your specific gravity is less than water, then your substance will float. It has a specific gravity that's less than water, it is less dense than the water, so it's going to float. For instance, if you put most metal, if you put a penny in water, it's going to sink because it has a higher specific gravity than water. But if you have a piece of wood, it's usually going to float because it's going to have a lower specific gravity than water. If the specific gravity of a substance is 1 or right at 1, then it will be buoyant. So it'll kind of bob around the top of the water. It won't float right above it. It won't sink to the bottom. It'll bob right around the top. So let's look at the specific gravity of our box over here. So we've got our density of the substance, which is 0.083 grams per cubic centimeter. And we have water, which is 1.000 grams per cubic centimeter. So your specific gravity would just be 0.083 grams per centimeter cubed, because at room temperature, water is going to be 1, and dividing by 1 is going to get you the same thing. So would this one, our box here, would it sink or float? Is the specific gravity less than that of water or greater than that of water? It's less than that of water. Less than specific gravity of water. So when it's less than that of water, it's going to float. So let's review all of these terms and make sure we understand the difference. The mass of our box was how much substance was in there. We had 10 grams of a substance in this shape. It weighed 1 pound. That was how much gravitational pull Earth had on the object. Its volume was based on its actual size, how much space it occupied, and it came out to 120 centimeters cubed, and we got that by multiplying length by width by height. Its density was mass divided by volume, so our mass of 10 grams divided by volume of 120 centimeters, and we rounded that to 0.083 grams per centimeter cubed because we were going to keep repeating forever with that 3. And then the specific gravity was just 0.083 grams per cubic centimeter as well, because at room temperature, water is 1 gram per centimeter cubed as well, and the density isn't going to change very much, so the specific gravity is just going to be the same as the density. Since our object's specific gravity was less than that of water, we know that it will float. Potential and kinetic energy. Potential energy is the amount of energy an object has stored due to its position or orientation. So potential energy is how much energy an object has when it's sitting still. It's just stored. It is not in motion. It's how much energy an object could have if it moved. It's potential energy. And gravity most commonly affects potential energy. Now there are other factors such as mass that can affect potential energy, but the force of gravity on an object is going to affect it the most. So if an object is up higher, it's going to have more potential energy than an object that's down lower, because the lower object is going to have a smaller amount of space to fall. The higher object is going to have a further way to fall, and so it's going to have more potential energy. The formula for finding potential energy, PE stands for potential energy, equals mgh. M stands for mass, G stands for acceleration of gravity, so the force that gravity is going to have on that object, and H stands for height. So you'll multiply the mass of the object times the acceleration of gravity times the height from which it is from the ground. And that is going to give you your potential energy. So you can see that the acceleration of gravity and the height, the distance an object is from the ground, are both big parts in this formula for finding potential energy. So gravity is very important to the potential energy in an object. So potential energy is how much energy an object has stored while it's sitting still. Kinetic energy is the energy of an object in motion. So when an object is actually moving, that is whenever you're seeing kinetic energy. And kinetic energy, Ke, can be found with this formula, mv squared divided by 2, where m equals the mass and v equals velocity. So mass times the velocity squared divided by 2 will give you the kinetic energy of an object. So this one doesn't have as much to do with gravity, because once it's in motion, the kinetic energy has more to do with the velocity and the mass of the object. So let's look at this. So we've got this little situation set up. You've built this out of wood or Legos or something, and you've got a ball and you're going to roll it down here. So when your ball is here, you have potential energy. It's sitting still. Once it goes over the edge, and you have it here, you have kinetic energy because this ball is in motion. If it moves down some more and sits still for a minute, you're going to have potential energy as it's sitting still, because it could still go down some more. And if it does, then you have kinetic energy again, because this ball is rolling, it's in motion. And then if it lands here, you've got potential energy again, because it can still drop off this ledge. So potential energy is energy that's stored while an object is still. Kinetic energy is the energy of motion. It's while something is actually moving. So potential is still and stored. Kinetic is moving, in motion.
Absolute zero is the temperature of 0 degrees Kelvin. But I first want to look at how we get to that temperature. All right, so kinetic energy of gas molecules causes motion and is measured by temperature. And when gas is cool, the kinetic energy of the gas molecules decrease, hence the temperature decreases. So let's go back up here. All right, so the kinetic energy of gas molecules causes motion. So it's the kinetic energy that makes things move, and this is measured by temperature. So it's not the temperature of something that causes something else. It's when gas molecules are in motion, we measure that amount of motion by temperature. Now think about gases cooling. Now don't think about it in terms of temperature. Don't think about it in terms of degrees. Just think about gases cooling. They're losing heat. So when gases cool, the kinetic energy of the gas molecules decreases as well. Now what did we just learn about the kinetic energy of gas molecules? They cause motion. So if the kinetic energy of the gas molecules are decreasing, then the motion is decreasing as well. And then because of that, temperature decreases, because the motion is measured by temperature. So if you think about molecules moving around and you can decrease the amount of motion they have, well, eventually, doesn't it make sense that at some point the molecules wouldn't be moving at all? Well, if the amount of motion of molecules is measured by temperature and the molecules aren't moving at all, then what would the temperature be? It would be 0 degrees. So that's how we get to absolute zero. Absolute zero is when the kinetic energy of a molecule is 0. And because the kinetic energy is 0, then molecular motion stops. And we measure molecular motion and temperature. So when molecular motion stops, we measure it in absolute zero, which is equal to 0 degrees Kelvin, K stands for Kelvin, or negative 273 degrees Celsius. Now, I didn't use Fahrenheit here because in science, we don't use Fahrenheit very often because that's not as important. So here we just have it in Kelvin or in Celsius. So 0 degrees Kelvin or negative 273 degrees Celsius is absolute zero. And that's when kinetic energy of the molecules is zero, and therefore molecular motion stops. Now, nothing can be colder than absolute zero because temperature is a measure of motion. And all motion ceases at absolute zero. So because the motion has all ceased and stopped, the motion can't stop anymore. So that's why absolute zero is absolute, because you cannot get any colder than that. Amorphous solids do not have a definite, regular, internal shape. Now, you may have heard of crystalline solids. Well, the main difference between crystalline solids and amorphous solids is that amorphous solids, like I said, do not have a definite, regular, internal shape. So this gives amorphous solids three interesting qualities. So the first is, when amorphous solids cool into a rigid form, they retain fluid-like properties. Now, because these amorphous solids have no definite, regular, internal shape, they can be easily molded. And so think about glass, for example. That's an example of an amorphous solid. And glass comes in a variety of forms and shapes. It can be a glass bottle, or it can be in a window, or it could be some kind of complex glass structure. The point is, glass can be molded into many different shapes and sizes. And there's other types of amorphous solids as well, like rubber, for example, which can be molded into automobile tires or sheets or gaskets. And there's also plastics, which can be molded into all types of shapes and sizes. So that's an example of how amorphous solids can be molded. Now, the third interesting characteristic of these solids is they do not break into regular crystals. And so remember how I was talking about glass as an example. You think about if you dropped a glass bottle, the different pieces of glass would not all be the same size. You would have some little pieces, some big pieces, and some in-between pieces. And again, that's just for example, because amorphous solids do not break into regular crystals. Now, if you think about crystalline solids, they do break into regular crystals. So again, there's another difference between amorphous solids and crystalline solids. But the main thing you need to remember is that amorphous solids have no definite, regular, internal shape. Avogadro's law shows that the volume of a gas is related to the number of molecules in it. It can be expressed in this equation, V divided by N equals K, where V equals volume, N equals number of moles of gas, and K equals a constant. Now, you know what a volume is, but you may be wondering what moles are. Well, a mole is the amount of a substance. 1 mole equals X amount of molecules. So the number of moles then is just a measure of how many molecules are in a substance. And then K is a constant, meaning it's unchanging. So like in this equation, K is always going to be the same number. Now, a more practical application of Avogadro's law is expressed in this equation. V divided by N1 equals V2 divided by N2. And this shows change over time. Now, there are other things that affect volume besides the number of moles. And there are other things that affect the number of moles besides the volume. So in order for this equation to work, the temperature and pressure must remain the same, because if the temperature and pressure are one thing here and then they change over on this side of the equation, then it's going to mess the whole equation up. So now I want to show you the practical application of this. Say we know that V1 equals 20 and N1 equals 4. And then we don't know what V2 is, but then the number of moles changes to 2. So the great thing about this equation is it helps us figure out change over time. So this is the same substance here. So the substance originally had this volume and this number of moles, and then the number of moles change. But since the volume and number of moles are related, remember we said the volume of a gas and the number of molecules are related, then when N1 changes to N2, V must also change because they're not just two separate entities, they're interrelated. So now we're just going to use algebra to solve. So 20 divided by 4 equals 5. We can multiply both sides by 2, and V2 equals 10. So I'm just going to replace V2 with 10 right there. So this is V1, this was N1, this is V2, and this is N2. So remember, N changed from 4 to 2, so V must also change. Now, what do you notice here? N went down, it decreased, and V also decreased. And they decreased by the same amount. Volume was cut in half, and the number of moles was cut in half. So we can say that volume and the number of moles are directly related. In other words, when V is cut in half, N is also going to be cut in half. So whatever happens to V is also going to happen to N. And whatever happens to N is also going to happen to V. So if V goes up, or increases, then N is also going to increase. And if V decreases, then N is also going to decrease. And it works the other way around. Say N decreases, then volume decreases. It doesn't matter which variable here initiates the reaction. The thing you need to take away from this is that volume and number of moles are directly related. So whatever happens to one is going to happen to the other. In solid molecules, the intermolecular forces greatly exceed the kinetic energies. So we're talking about solids here. And here the intermolecular forces are the dominant force. And the intermolecular forces hold the molecules tightly together in tightly packed arrangements. And so these solid molecules can be packed in many different arrangements. This gives solids definite shapes. And these solid shapes fall into two categories: crystalline solids and amorphous solids. Crystalline solids are when the molecules are arranged in orderly, repeating patterns. So an example would be in a gemstone or any other type of mineral. There's some kind of sequence here. You can figure out what's going to come next because there's an order to it. Then there's also amorphous solids, which are basically the opposite of crystalline solids. Here, the molecules lack a regular internal structure. There's no sequence to it. And these molecules are more like supercooled fluids, and the molecules have been permanently frozen. An example here would be glass or rubber. So these are the two main categories of arrangements that shapes can fall into. I want to take a look at 4 of the basic properties of gases. And I want to talk about the properties of gases in the context of a balloon so that it gives us something to visualize when we're talking about these properties. So think of a balloon, and as you blow air into this balloon, you're adding molecules to the air. As more of this air gets added to the balloon, the volume is going to increase, which makes sense. Everyone knows when you blow air into a balloon, the balloon expands. And if you let air out of the balloon, then the balloon gets smaller. So volume is proportional to the amount of gas. Now, for this to be true, the temperature and the pressure has to be constant. And you may be wondering, why is that? Well, you'll see later that temperature affects the volume and the pressure affects the volume. So if the temperature and pressure are changing, then they're also affecting the volume in addition to the amount of gas, and we can no longer really see what's really affecting the volume. So volume is no longer proportional to the amount of gas. But if temperature and pressure are constant through this entire time, we can pretty much take them out of the equation because they're not affecting anything anymore because they're not changing. So when temperature and pressure are constant, we can then say volume is proportional to the amount of gas. Now, the second property of gas is also very interesting. If you think about a balloon that has a fixed amount of air in it, in other words, the end's tied off. You can't add air, you can't remove air. And then you heat this balloon, it will expand. The volume will increase. As you heat it, the balloon will get bigger. Now, if you cool the balloon, then the volume will decrease. The balloon will get smaller. So we can say the volume changes directly with temperature. As temperature increases, volume increases. And as temperature decreases, volume decreases. Now, for this to be true, the pressure of the balloon has to remain constant throughout the entire process. Now, if you squeeze the balloon, the volume will decrease because gases are compressible. So we can say the volume changes inversely with the pressure. And this makes sense. Okay, so say there's lots of pressure. You're pushing really hard on this balloon. The volume is going to decrease. So at that point, the pressure is increasing because you're pushing harder, but the volume's decreasing. And if the pressure decreases and you're not pushing as hard, then the volume will increase. So that's why we say volume changes inversely with the pressure. And for this to be true, the temperature has to remain constant. Now, the fourth and final property of a gas. If you fix the volume of the balloon and add more air, then the pressure inside will increase. So we can say pressure changes directly with the amount of gas. And this makes sense because you think about air molecules inside that balloon. They're moving all over the place. Well, if volume, or if the amount of gas is large, then the molecules are going to hit the sides very often. Okay, so you think about the volume being the same throughout this whole time. The balloon is always going to be the same size. But if you add more air to it, then there's more air molecules that are going to hit the side of the balloon more often. So that increases pressure. But if there's less air inside that balloon, then the air molecules are going to hit the sides of the balloon less often, which decreases the pressure. So that's why we say pressure changes directly with the amount of gas. Now, for this to be true, like I said, the volume has to be constant and the temperature also has to be constant. So those are the four basic properties of gases. Charles's law shows the relationship between volume and temperature. But in order for Charles's law to be correct, the pressure and the amount of gas must remain the same. They must remain constant. Charles's law can be expressed in the equation V equals K times 2, where V equals volume, K is a constant, meaning it's always the same, and T is the absolute temperature, expressed in kelvins. So say the constant was 2, I'm just making that number up, all right, and the temperature is 5, and the volume is 10. That equation makes sense. So this is the volume, this is the constant, this is the temperature. Now say the volume is 6. Well, the constant's going to have to be the same because it's always the same, times T. I'm trying to figure out what temperature is going to be. Using algebra, we divide both sides by 2, and T equals 3. So now, I'm just going to erase all this real quick. T equals 3. So volume went down, and so did temperature. So we can see here that volume and temperature are directly related. In other words, what happens to one variable will also happen to the other. If volume decreases, temperature will decrease. If temperature decreases, volume will also decrease. And if volume increases, temperature will increase. And if temperature increases, volume will also increase. Now, I want to look at a more practical application of Charles's law. We can also express Charles's law like this. V1 divided by T1 equals V2 divided by T2. Now look at this example problem. A 2.0 liter balloon is at a temperature of 223 Kelvin. When the balloon is heated to 323 Kelvin, what is the volume? So this is the first volume right here, so that's V1. It's at a temperature of 223, so that's T1. Then the balloon is heated to 323, so that's T2. And then what is the volume? So V2 is what we're looking for here. So we need to get V2 by itself on the side of the equation. Now notice here that the temperature changed. It went from 223 to 323. So since volume changed, temperature also has to change here. Or excuse me, since temperature changed, volume also has to change here. So that's why we're looking for V2. And notice that temperature went from 223 to 323. So it increased. So we can also know that volume is going to increase. And we'll see that in a moment once we work this equation. So we're going to multiply both sides by T2 to get V2 by itself on the side of the equation. So then we're going to do V2 equals, all right, T2 is 323K times V1, which is 2.0 liters, then divided by T1, which is 223 K. Now, I'll save you having to do all the math, so the answer is 2.90. Now, we have to put the correct units on here. We can cross out the K's, so the only thing left is the L, and that should be correct because volume is always expressed in liters. It's never going to be expressed in a temperature unit. All right, and so notice here the volume was originally 2, and now it's 2 9/10. And the temperature was originally 223, and now it's 323. So temperature increased, and since temperature and volume are directly related, volume also increased. Now, Charles's law makes sense because imagine a balloon filled up with molecules of a certain gas. Well, if that gas is heated up, then the molecules start moving faster. And when the molecules start moving faster, they start bumping up against the sides of the balloon more often. And they start pushing the walls of the balloon out, increasing the volume of the balloon. Now, if the balloon is cooled off, then the molecules inside start moving slower, and they don't start hitting the sides of the wall as often. So since they're not hitting the sides of the wall as often, the walls start to come in, and the volume decreases. So that's a practical application of Charles's law. So the important thing to remember is that volume and temperature are directly related. The three laws of thermodynamics are important to our understanding of energy and heat. So I've written each law up here on the board, and then under each law, written a brief summary of that law. So the first law of thermodynamics says that energy is always conserved. So take, for example, when I rub my two hands together. So I'm rubbing my hands together. So I'm exerting energy to rub my hands together. So it would look like my body is losing energy because I'm having to exert that energy to rub my hands together. But because I'm rubbing my hands together, I'm creating friction, which creates heat, and I can feel my hands getting warm right now. So although energy is coming out of my body to rub my hands together, it's changing forms into the form of heat. So heat is another form of energy. So energy is always conserved. It may change forms, but the energy is always there. You can't destroy energy. The second law of thermodynamics is that a system will develop a uniform temperature. So say I had a box, and inside that box I had two blocks of metal, and the blocks of metal were of equal weight. The first block of metal weighs 100 degrees, and the second block of metal weighs, the first block of metal is 100 degrees, and the second block of metal is 0 degrees. So eventually those two blocks are going to balance each other out until both blocks weigh 50 degrees. So that's basically the second law of thermodynamics, that both blocks in the box are going to work together to find one temperature, an equilibrium, a temperature that each block is going to have. So this can be applied to many different things, any sort of system that you have where you have different objects inside that system and they have different temperatures. Eventually all the objects in that system are going to have the same temperature. The third law of thermodynamics is that entropy becomes constant as temperature approaches 0. Now this doesn't really make sense unless you know what entropy is. Entropy is the flow of heat. So as the temperature approaches 0, the flow of heat becomes constant. So that's a look at the three laws of thermodynamics and how they affect our world. A magnet is basically just a substance that has a magnetic field. Now the magnetic field isn't visible, you can't see it in the air, but you can see the results of it. Take a refrigerator magnet, for example. It attracts the refrigerator door to itself, and so you can see the result of the magnetic field because the magnet is sticking to the refrigerator door. You can also see the results of a magnetic field when two magnets interact with each other. You may have noticed that if you put two magnets near each other, they are attracted to each other and come closer to each other. But then if you turn one of the magnets around, they repel each other and push away from each other. When talking about magnetic materials, we refer to the materials as ferromagnetic because they have the ability to have a magnetic field. And within the category of ferromagnetic materials, we have soft materials and hard materials. A soft ferromagnetic material, some type of material that responds to a magnetic field and will have that magnetic field for a little bit, but quickly loses it. Now, every substance on Earth in some way responds to a magnetic field, but soft ferromagnetic materials are the ones that respond a little bit more to that magnetic field. Now, a hard ferromagnetic material is some kind of material that responds very well to a magnetic field. It takes on that magnetic field and contains it for a long time. Permanent magnets are made out of hard ferromagnetic materials because they're given a magnetic field and they keep it, and it's really hard to take away that magnetic field from that substance, such as a refrigerator magnet. It's been magnetized and it's hard to unmagnetize it. There's also something involving magnets called an electromagnet. An electromagnet is basically a coil wrapped around some sort of soft ferromagnetic material. So when electricity is turned on, the coil becomes magnetized, and when you turn the electricity off, it no longer has a magnetic field. The soft ferromagnetic material that it's wrapped around is generally steel, and so again, just when you turn the electricity on, the coil and the steel inside of it exert a magnetic field. Then when you turn the electricity off, they no longer have a magnetic field. So those are some of the important things to remember about magnets. Organic compounds are basically compounds that contain carbon. There are two main ways to classify organic compounds. The first is by classifying where they come from. So you would have natural organic compounds and synthetic organic compounds. The second classification system is based upon how large the compounds are. So you have small molecule and polymers. In this case, we're going to take a look at the first classification system. So natural compounds are just what the name implies, compounds that can be found naturally in nature. So these natural compounds are produced by plants and animals, and humans take those compounds and use them for their own use. Sugar is a great example of a natural compound because it's naturally occurring in nature because it's produced by plants. Synthetic compounds are produced by humans, and humans produce it and then use it for their own use. Now, sometimes these synthetic compounds can actually also be produced by nature, but for whatever reason, industry has found it more efficient to produce it synthetically. A great example is rubber. Rubber can be produced naturally by plants, but industry today finds it more efficient to synthetically produce rubber. So that's a quick look at organic compounds and how they can be divided up into natural organic compounds and synthetic organic compounds. The periodic table is a way to systematically display the chemical elements. Now notice I said that it consists of chemical elements, and it consists of elements only. So this does not include mixtures and compounds, because an element is basically matter in its most basic form. The periodic table positions chemical elements based upon atomic number. An atomic number is the amount of protons an atom has in its nucleus. So hydrogen is the first element on the periodic table because it has one proton in its nucleus. And then the next chemical element has more protons in its nucleus. Like I said, the periodic table arranges chemical elements very systematically. So if you were to take a look at one row on the periodic table, all of the chemical elements on that one row would have the same number of electron shells. And if you were to take a look at one column, all of the chemical elements in that column would have the same electron configuration. So the periodic table arranges the elements in such a way that all the elements are next to similar elements. So if a scientist knew a lot about one element, he could know a lot about the elements around it just because all the elements are grouped together with similar elements. There are about 118 elements out there, but only 114 have been officially recognized. And 98 of those are natural elements, ones that naturally occur in nature, such as potassium, nickel, and hydrogen. The other ones are synthetically produced by humans, such as Einsteinium. So the important thing to remember about the periodic table is that it consists of chemical elements and it is arranged by atomic number. pH is basically a measure of how many hydrogen ions are in a substance. pH is very important to many fields such as biology, chemistry, medicine, food science, farming, and water treatment. I've written up here on the board a pH scale ranging from numbers 0 to 14, each indicating the amount of pH in a substance. Now there are pHs that go higher than 14, but for practical purposes, this is the largest pH scale we need. Water has a pH of 7, and any substance with a pH larger than 7 is considered a base. So everything from 7 over to 14 is considered a base. Common bases that you probably know of are baking soda and bleach. Now, any substance with a pH below 7 is considered an acid. Some of those that you may know of are lemon juice, tomato juice, and gastric acid. So water is kind of the middle bar on the pH scale, and anything to the right is the base, and anything to the left is an acid. The scientific method is a process that has been around for over 1,000 years that is used by scientists to make scientific discoveries. There's a progression in the scientific method. The scientist starts by asking a question that the scientist wants to have answered. In this case, the question is going to be, which cat is faster? The scientist is interested in knowing if the lion or the cheetah is faster. Then the scientist, based off of prior knowledge, is going to formulate a hypothesis. In this case, the hypothesis is going to be the cheetah is faster. Notice how the hypothesis is written as an established fact. It's because through the experiment portion of the scientific method, the scientist is going to try to prove his hypothesis true. Then comes the prediction portion of the scientific method. In this portion, the scientist is going to try to clarify his hypothesis. So in this case, the prediction is going to be the cheetah will be faster over a 60-meter period. It's important to realize the difference between a hypothesis and a prediction. A hypothesis is stated as established fact, and the experiment is either going to prove or disprove the hypothesis. The prediction clarifies the hypothesis because otherwise the experiment could just prove that the cheetah is faster over a 2-meter period, but that doesn't really show any endurance on the cheetah's part. So the prediction says that the experiment results are going to show that the cheetah will be faster than the lion over a 60-meter period. Then comes the test portion of the scientific method. This is very important. This is the experiment part of the scientific method. This is when the scientist either proves or disproves his hypothesis. So I'm going to write here that the scientist is going to use a radar gun. So the scientist is going to point the radar gun at a cheetah running over a 60-meter period and write down how fast the cheetah was running, and then point the radar gun at a lion running over a 60-meter period and write down the speed of the lion. Then comes the analysis portion of the scientific method. This is when the scientist looks at the results and decides whether they prove or disprove the hypothesis. So in this case, the analysis is going to prove and confirm the hypothesis. So I'm going to write here that the hypothesis is confirmed, because the results of the experiment showed that indeed the cheetah was faster than the lion. So if my example confused you a little bit, don't worry about it. The important thing to remember is the main points of the scientific method: the question, hypothesis, prediction, test, and analysis.
Temperature scales and conversions. There are 3 main scales for measuring temperature. First, we have Celsius. Celsius uses the base reference points of water freezing at 0 degrees and boiling at 100 degrees. So the Celsius temperature scale is based around water's freezing and boiling points. Next, we have the Fahrenheit scale. Fahrenheit uses the base reference points of water freezing at 32 degrees and boiling at 212 degrees. So Fahrenheit also uses water's freezing and boiling points as base reference points, but its scale is different. You can see the degrees for water's freezing and boiling points are higher in the Fahrenheit scale than in the Celsius scale. The third main scale for measuring temperature is the Kelvin scale. And Kelvin is an absolute temperature scale. This means its 0 mark corresponds to absolute 0. It isn't based on the freezing or boiling point of water. It is based on absolute 0, where that starts and then goes up from it. And absolute 0 is the coldest possible temperature. So absolute 0 is the coldest possible temperature. It's going to be 0. And working up from there, we get to water's freezing point at 273.15 Kelvin. And its boiling point at 373.15 Kelvin. Kelvin does not use degree terminology. So where we would say degrees Fahrenheit or degrees Celsius, we would just say Kelvin with the Kelvin temperature scale. So where Kelvin is an absolute temperature scale based on absolute 0, and it's more corresponding to the laws of thermodynamics than to how any other substance behaves, Celsius and Fahrenheit are both relative temperature scales. They were developed relative to the freezing and boiling points of water. And clearly the scales did develop differently, since Celsius says it freezes at 0 and boils at 100, and Fahrenheit says it freezes at 32 and boils at 212. So now that we've talked about our 3 main scales, Celsius and Fahrenheit, which are relative to water's freezing and boiling point, and Kelvin, which is based on where absolute 0 is, let's look at how we can convert between these 3 main scales. You are not likely to see any temperatures given in a measurement other than Celsius, Fahrenheit, or Kelvin. So it's important that you learn these 3 and then learn how to convert between the 3 in case you are trying to get Fahrenheit and you've been given Kelvin. So first, let's convert Celsius to Fahrenheit. The formula for that is to plug in your Celsius temperature and do 9/5 times your Celsius temperature plus 32. And that'll give you your degrees Fahrenheit. And that makes sense that you're multiplying by a mixed number, which is going to give you something bigger, and adding 32, because your Celsius temperature starts lower than your Fahrenheit temperature. So if we were to say 0, if we had 0 degrees Celsius, 9/5 times 0 is 0, plus 32 is 32, well, 0 degrees Celsius equals 32 degrees Fahrenheit. And that makes sense because they should both be the same, since they are saying that at that equal temperature is when water freezes. It freezes at 0 degrees Celsius, it freezes at 32 degrees Fahrenheit, so it makes sense that they would both, that translating 0 degrees Celsius would equal 32 degrees Fahrenheit. They should be an equal temperature because they both are representing when water freezes. Let's look at a different temperature, 50 degrees Celsius. So let's plug it in. We'll have degrees Fahrenheit equals 9/5 times 50 plus 32. Okay? 50 times 9 is going to be 450, because 9 times 5 is 45, and then we just add that 0 onto the end. And then we have to divide by 5. Dividing by 5, 5 goes into 45 9 times, and we can carry that 0 up there. So 9/5 times 50 is 90, and we need to add that to our 32. 2 plus 0 is 2, 9 plus 3 is 12. So 50 degrees Celsius equals 122 degrees Fahrenheit. So if you were to hold something that was 50 degrees Celsius, it would also be 122 degrees Fahrenheit. And you probably wouldn't want to be holding it because that would be pretty warm. Okay, next let's convert Fahrenheit to Celsius. Again, if we said 32 degrees Fahrenheit should equal 0 degrees Celsius, if we plugged in 32 degrees Fahrenheit, minus 32 would be 0. 0 times 5/9 would be 0, and so 32 degrees Fahrenheit would equal 0 degrees Celsius. Let's look at 50 degrees Fahrenheit. Let's convert that to degrees Celsius. So we're going to plug in degrees Celsius equals 5/9 times 50 minus 32. Okay, so 50 minus 32 is 18, and we need to do 18 times 5. 8 times 5 is 40. 5 times 1 is 5, plus 4 is 9. And then 90 divided by 9 equals 10. So 50 degrees Fahrenheit equals 10 degrees Celsius. So if you can remember these formulas, then you will be able to convert Fahrenheit to Celsius and Celsius to Fahrenheit. And you can see they're very similar. 9/5 times Celsius plus 32, 5/9 times Fahrenheit minus 32. And you have to do the taking away 32 before you multiply times 5/9. Otherwise, your answer is not going to come out the right way. So let's look at converting Celsius to Kelvin. There's no direct formula for Fahrenheit to Kelvin. It would just be basically combining the Fahrenheit to Celsius and then Celsius to Kelvin. So it would be best to do it as a two-step process. So if we have 50 degrees Celsius and we want to convert it to Kelvin, we're going to plug in over here. Degrees Celsius, 50 plus 273.15, and we're just going to add them together. So let's put 50 over here so it's all nice and lined up. And we get 323.15 Kelvin. And remember, we don't use degrees with the Kelvin scale. Converting Kelvin to Celsius is just the opposite. You take the Kelvin temperature and subtract 273.15. So our degrees Celsius is going to equal, if we're using 350 Kelvin, 350 minus 273.15. We need to go ahead and put some zeros on there so that we can subtract the decimal. Borrow our way across. 10 minus 5 is 5, 9 minus 1 is 8, 9 minus 3 is 6. We got to borrow again. 14 minus 7 is 7, 2 minus 2 is 0. So 350 Kelvin equals 76.85 degrees Celsius. And with Celsius, we do say degrees. It is a degree-based scale. So 76.85 degrees Celsius is equal to 350 Kelvin. Remember, your three main scales for temperature are Celsius, Fahrenheit, and Kelvin. Celsius and Fahrenheit are based on when water freezes and boils, where Kelvin is based on absolute zero. And then try to memorize these formulas to be able to convert between Fahrenheit and Celsius, and then between Celsius and Kelvin, so you can get the temperature that you need. Velocity and acceleration. Velocity is the rate of motion, or speed, in a specific direction. This means that velocity is a vector. We need both its magnitude, or value, and its direction. If we only know the speed, that is not the velocity. We have to also know the direction. So if we just know we're going 30 miles an hour, that is only our speed. If we know we're going 30 miles an hour in a southwest direction, then our velocity is 30 miles an hour southwest, and that is a vector. Average velocity is one of the two velocities that you need to keep in mind. Average velocity is found by dividing the distance traveled by the time traveled. So your formula would be velocity equals distance over time. So you may start slow, speed up, and then slow down as you come to your destination. So from point A to point B, how far you traveled is going to be your distance So let's say you traveled 120 miles. And you were traveling southwest. And it took you 60 minutes to get there. Then you would divide that. 120 divided by 60 equals 2. So you were going 2 miles per minute southwest. And that would be your velocity, 2 miles per minute southwest. Now, if we were trying to do that in hours, we could have just changed it to 1 hour, and that would have been 120 miles per hour. So that is really fast, and not a likely velocity. But if something was going that fast, its velocity would be 120 miles per 1 hour southwest, or 2 miles per minute southwest. And it's important to include the direction, otherwise you only have speed. The fact that you have direction is what makes it velocity. So your average velocity is how far you traveled divided by how long it took overall for the whole trip. Your velocity is constantly increasing and decreasing as you're traveling. The other type of velocity to look for is instantaneous velocity. And this refers to an object's velocity at an exact second in time, and usually requires the use of calculus to be determined. But if you hit a pothole, it would be good to know if you were going 1 mile an hour or 60 miles an hour. And so knowing at that exact second in time how fast you were going, in what direction, that would be important. So sometimes you might have to find instantaneous velocity, but most commonly, average velocity is what you hear about. Now, acceleration is the change in the velocity of an object. Acceleration is also a vector and will have both magnitude, a value, and direction. And remember, we talked about your velocity would be increasing and decreasing as you traveled. Well, acceleration is the change in that velocity. So acceleration points the same direction as velocity while you are maintaining or increasing speed. So velocity is going this direction, acceleration is going this direction while you are maintaining or increasing speed. Deceleration is another word for acceleration when you are losing speed, when your velocity is decreasing. So deceleration is going to point in the opposite direction as velocity. So if you're going this direction but you're slowing down, then velocity still points this way, you're still traveling this way, but your acceleration is decreasing, your velocity is decreasing. So when you're decreasing speed, acceleration is going to go in the opposite direction of velocity. Your velocity is always going to stay the same way because you're going to be traveling forward in time. Now, deceleration is still referred to as acceleration because remember, acceleration is a vector with magnitude and direction. So it's going to point backwards, opposite of velocity, whenever you're decreasing speed or decelerating. It's going to point forward in the same direction as velocity whenever you're maintaining or increasing speed. So sometimes the word deceleration is used, sometimes it's not. Sometimes it's just acceleration both ways. So it's important to know that it can still be called acceleration even whenever you're decreasing speed. And this is the way that it would look if it was represented with vectors. So now let's look at our example over here. You've got velocity over time here, and this arc is your distance. You start out with a low velocity and build up, and then you slow down as you come to your destination at the end. So you can see your velocity is still going in this direction, increasing, and your acceleration is increasing in this direction. Up at the top, velocity and acceleration are both pointing in the same direction. And then as you start to slow down, velocity is still going to go in the same direction because you are moving forward in time, and even while you're slowing down, velocity is going to point in the same direction moving forward. But acceleration points backwards now because you are slowing down. So as your velocity decreases, acceleration is going to point opposite of the velocity. So this would be your distance covered, this whole line, and you would divide by this time here to find your average velocity. But instantaneous velocity would be if you said right here at this point, I want to know what my velocity was. So velocity is your rate of speed in a specific direction. Your average velocity is found by dividing the distance you covered over the time it took you to cover it. Instantaneous velocity refers to an object's velocity in an exact moment in time. And acceleration is the change in the velocity of an object, either as it increases or decreases, because acceleration is also a vector and will have both a value and a direction. So it will face the same direction as your velocity if you are increasing speed, and it will face the opposite direction if you are decreasing speed. Work. Work is the amount of energy expended in accomplishing a goal. The simplest equation for work is W equals FD, which means F times D, and that is where F is the amount of force exerted, and D is the displacement of the object upon which force is exerted. So, work is going to equal the force times the displacement, how far the object moved. This equation requires that the force be applied in the same direction as the displacement. If force is exerted in the same direction, then this formula will work. If force is applied in a different direction, you might have to alter your formula. So, if we had this boulder and force was exerted forward and the boulder moved forward and was displaced this distance, we could say work equals the force used to push the boulder times its displacement, because force and displacement went in the same direction. Now, if this is not the case, work may be calculated a different way. It can be calculated using the formula W equals FD cosine of theta, which means force exerted times the displacement times the cosine of theta, where theta is the angle between the force and displacement vectors. So, the angle between the direction force was going and the direction the displacement actually went. So let's look at our boulder again. Let's say we pushed at this angle and the boulder moved forward along the ground. Well, this angle between the displacement vector and the force vector would be theta, and we would plug that into our formula to figure out the actual work done. Now, if force and displacement have the same direction, work is positive. So this would be an example of positive work. If force and displacement have opposite directions, work is negative. So an example of that would be if someone were over here, if we had the same displacement, but some person was over here and they had a lever system, like a lever and pulley system going, and they were able to pull the boulder toward them. So if they were able to pull the boulder toward them, they would be exerting force from over here, but they would still be displacing the boulder this way. So if they were exerting force this way while displacing this way, the work would be negative. So force going to the left, displacement actually going to the right, that would be negative work. And if force and displacement directions are perpendicular, work is 0. So the work done would equal 0. And that means no work is done. An example of that would be the ground pushing up on the boulder. The ground has its own force pushing up on the boulder. If the boulder is moved to the right, the ground's force against the boulder did not affect the displacement, and so no work was done by this force. So even though the boulder moved from here to here, the ground remained pushing up against the boulder, and no work was actually done by this force. Work is measured in joules, and a joule is the work expended by a force of 1 Newton through a distance of 1 meter. So if you exert 1 Newton of force through a distance of 1 meter while you're pushing an object 1 meter, that is equal to 1 joule, and work is measured in joules. So when you're multiplying and using this formula, force is going to be measured in newtons. Your displacement should be measured in meters. So if you need to translate between different units to get your force to newtons and your displacement to meters, then please do so. And then you will get a joule, or number of joules, as your answer for how much work was expended.
We're going to take a look at electrical force. So first we need to define electrical force. So it's a universal force that exists between any two electrically charged objects. So it's a universal force that exists between any two electrically charged objects. So notice it's universal, so it applies to any objects that are electrically charged. So opposite charges attract one another, and like charges repel one another. This may be a concept you're already familiar with, but if you have a positive charge here and a negative charge here, they are attracted to each other. They're trying to pull towards each other. But if you have two positive charges, they're trying to repel each other. They're trying to get away from each other. It also works with two negative charges. You have negative charge here, negative charge here. They're trying to get away from each other. Now, there is an equation we use to determine electrical force. So first we have F. We're solving for F. That stands for the electrical force. And it equals K times Q with the subscript of 1, Q with the subscript of 2, divided by radius squared. So K here is a constant. It's 9 times 10 to the 9 radius meters over C squared. And then Q1 and Q2 stand for the magnitude of the charge. Because remember, the definition says this is a force that exists between two electrically charged objects. So we have to have two objects here. So this right here stands for the first object. This here stands for the second object. And so they stand for the magnitude of the charges. And then finally, we have R right here. In this case, it's going to be R squared. So I'm just going to write R here, which stands for the distance between objects. You can think of this as standing for radius. So we have positive charge here and a negative charge here. And say they're 2 meters apart. There's 2 meters in here. And the radius would be 3 meters. And then Q1 and Q2 are going to change depending on the magnitude of the charges, but K is a constant, which means it's going to be constant. It's always going to be there. Now, magnetic forces operate on similar principles. So if you understand this, then you can also kind of understand magnetic forces. Now, I want you to notice something interesting about the equations here. To help you better understand it, I'm going to write it like this. So F equals K times Q1 times Q2 over R2. So we have the division symbol in the horizontal here, which makes it easier to see. So the magnitude of the force is directly proportional to the magnitude of the charge. So Q1 and Q2 are directly proportional to F. So as these get larger, it means the numerator is going to be larger. And you have a larger numerator over the denominator, the result is something bigger. Like if you have theta over 2, you get 4, but then say Q1 and Q2 increase to get 10, 10 over 2 equals 5. So Q1 and Q2 are directly proportional to F. However, F is inversely proportional to the square of the distance between the two objects. So electrical force is inversely related to the square of the distance. That's because as the denominator gets bigger, what you get right here gets smaller. Okay, so right here you have 8 over 2 that equals 4, but then say the fraction changes to 8 over 4. The denominator gets bigger, now you end up with 2. So now the constant right here is always going to be the same, so you don't really have to worry about that. But as these get higher, F gets higher. But as this gets higher, F gets lower. Now if Q1 and Q2 got smaller, then F would get smaller. But if R squared gets smaller, then F gets bigger because they have an inverse relationship. So that's a look at electrical force. We're going to take a look at 3 different terms you're going to come across when discussing circuits. So the first is electric potential, which is an expression of potential energy per unit of charge. And so we basically have 2 types of energy, potential and kinetic. So potential energy is stored up energy, and kinetic energy is energy in motion. So this is electric potential. So it's electric energy that is stored up that can be used. Now, electric potential, or what we could also call electrostatic potential or voltage, is measured in volts as a scalar quantity. And so the formula is V equals E over Q. So V, of course, stands for voltage, E stands for the electrical potential energy, and Q stands for the charge. Next, we have voltage, which is electric potential difference between 2 points in a circuit. So it's the electric potential difference between 2 points in a circuit. Now, voltage can also be thought of as a measure of the rate at which energy is drawn from a source in order to produce a flow of electric charge. And so the rate of flow of electric charge is expressed using the amp, and it can be measured using an ammeter. So 1 amp is equal to 1 coulomb, or what we could abbreviate as capital C. It's equal to 1 coulomb of charge passing through a given area in a second. So 1 coulomb of charge passing through a given area in a second. And then we have electric charge, which typically only moves from areas of high electric potential to areas of low electric potential. So we have electric charge, which moves from high electric potential to low electric potential. Now, to get charges to flow into a high potential area, you must connect it to an area of higher potential by introducing a battery or other voltage source. So say you have an object right here which has, or this is an area of low potential energy, of low electric charge. And then over here you have another area that has high electric charge. So naturally, electric charge is going to want to move from this area of high electric potential to this area of low electric potential. Now, if you want to get this electric charge to move in this direction, that's when you're going to have to introduce a battery or other voltage source. And that's the only way you're going to be able to get this low electric potential, or the only way you're going to be able to move this electric charge from this area of low electric potential to this area of high electric potential. So that's a brief look at electric potential, voltage, and electric charge.